Can you see my screen?
Yep, you're good.
Okay. I think we're ready to get started. So hi, everybody. Welcome back to another class in spring 2021, 18S191-6S083, computational thinking at MIT. So today we're going to talk about random walks. We've been talking quite a lot about different kinds of ways of thinking about randomness and modeling that in the computer. And this is a particularly interesting, in my opinion, I like this subject a lot. And it's very useful to model many situations in engineering, science, finance, etc. So I'd like to start off by, let's think about, so what is a random walk? And then why is it useful? So let's just start off by visualizing a random walk. So here I've got a particle and it's living in 2 dimensions and it's just going to jump at each step to a neighboring site. So it can move up, left, right, or down on this grid that you can see. And so as I move this slider, we're going to see that dynamics happening. So there it moved up, then it chose to move down, then it chooses to move down again, left, etc. So basically at every step, it chooses one of the 4 directions with uniform probability, equally likely. Okay, so that was just 10 steps. What if I take more steps? So now I'll just let's take 100 steps instead, and it does something like this. Okay, so it just literally is dancing around at random. Now let's increase the number of steps a bit, and now it looks more like this. So you can see that it's still, you can still see the kind of graininess of moving on this lattice or grid, but it's starting to look, you've almost lost that graininess actually. And if I increase the number of steps, but I'm still plotting it kind of within the same window, same sized window, then actually you can basically no longer see that it's actually moving on a grid, and it's just moving around at random. So now let's look at another system that's actually completely different, which is a lot of hard disks bouncing off each other. So just a minute, let me get that set up. So can you see this this visualization now?
Yep, and we see your Slack too.
Yeah, sorry about that. Okay, let me close that. So, okay. So here we have just a large number of hard disks, and we're going to put them in to move. So each of these disks you can think of as a molecule moving around. So this is really a visualization of a gas, of the molecules in the air in your room or in a fluid moving around. And each of them is following Newton's law. So it's just basically there's moving in a straight line until it meets another disk, and then it collides with that disk and bounces off in a way that conserves energy. So I'm going to actually label those disks. And I'm going to follow one in particular, and I'm just going to draw its trajectory as it's moving around and bouncing off these disks. And let's speed that up a bit. This is all in real time. And then I'm actually going to, so you can see that, yeah, indeed, this dynamics is being generated by this particle being buffeted, being moved around by these other disks. Now I'm just going to turn those other disks off, and we'll just look at that particle doing its thing. And if you did not know what the underlying dynamics was, you would say, oh, that particle is just moving at random. So what is the origin of randomness in physical systems, at least? It's actually that we have all of this other stuff going on in the system, and we don't know about it. And so that's effectively giving us something that looks random, at least. So this is basically you would think that this particle was jumping around at random, choosing random directions at each step. And so, this trajectory actually looks a lot like the other trajectory that I already drew.
I think
that
that's
this
the path
trajectory
that
is actually random. Sorry?
I feel like that's the path that I'm forced on when I get off the subway during rush hour.
Yeah, exactly. So, so this kind of process, random walks, is so this is as I said, a random walk is jumping at random, and what I'm saying is that actually we can find behavior that looks like that in many systems, physical systems, the stock price. So let's just go and look at the Apple stock price, for example, whichever stock price. I'm just going to do a Google search for Apple stock, and then we'll look at sort of 1 year's worth of stock prices, and you can think that this is some kind of random walk as well. So of course it's not completely random, because at the start of this year it was just drifting upwards with some randomness on top. So it's not doing exactly the same thing as we're modeling. And so the question is, well, can you actually predict that particular piece of the motion? And people make and lose billions of dollars a day doing that. Okay, so let's go back to, it's so difficult to keep track of where all these windows end up. Sorry.
By the way, did you want to review what Julia concepts we're going to learn today?
Yes, good idea. If I can find my window, that would be helpful.
Meanwhile, we could look at the Apple stock price over the past year.
Sorry, just completely lost where the actual window is.
My kids keep telling me I have way too many tabs open on my screen.
Yes, that is always my problem. But I mean, I had it all carefully planned, and then, it all starts going on. Okay, this seems to be it. Okay. Is that the right version?
You had it, and then it disappeared.
No, that's not the right one. Ah.
I'll just mention while you're looking that when I was an undergraduate, almost everybody was reading this book called A Random Walk Down Wall Street. I think it's still maybe a very popular book. So by Malkiel. So in case you were wondering whether random walks were relevant to stock prices, that book kind of said that everything was basically a random walk.
Yeah. So basically, we're going to look at how we can, implement random walks, and that's going to involve various different concepts. So the first thing we're going to do is look at how we can. So when we want to generate a random walk, we want to do jumps left and right. So there are various ways we can implement that, and we want to actually compare them maybe to see which is going to be the most performant, the fastest solution in Julia to do that. So we're going to use this package called Benchmark Tools, which is provides a very nice interface to just quickly benchmark a small piece of code called a micro benchmark. We're going to plot several random walk trajectories. And so in order to do that, we want to have a loop, and inside the loop, we want to plot over and over again and sort of add onto the same plot different trajectories. So if you've actually tried that in Julia, you'll realize that that's not actually, there's some trick to it. So I'll discuss that. We'll talk about a very important concept, which is generic programming. So I want to write a single piece of code, which is generate a random walk trajectory, and then I want to run it for different types of random walks. So this is very similar to what we did last lecture, where we had different random variable types, which we can sample from. And we're going to look at, so when we create those random walk objects, we need to change their values somehow. So we could do that by changing what's inside them, or by creating new ones. So that's the concept of mutability versus immutability. And then we want to run a function with a type as a parameter. And so we'll introduce this Julia word where and see how that works. And we'll need vectors of vectors, so which is we'll have a vector that will be evolving in time, and so we need to store all of the time evolution of all of those vectors inside something, and that something is going to be just another vector. And we'll talk about aliasing of memory, which is when two different names point to the same place in memory, and the cum sum function, which is for cumulative sums. Okay, so we've seen the motivation. So this two-dimensional random walk is, so by the way, later on we're going to talk about discrete versus continuous. So you can see that as I increase the number of steps, I'm actually, you're sort of losing, as I said, losing the fact that we're living on a discrete mesh or grid or lattice. You're losing that information or losing that fact. And so you can see that in some sense we're converging to some kind of random process which doesn't know that there's a grid there, and it's just taking little steps of different sizes in different directions. And that's actually called Brownian motion. So the original physical the physical discovery by Brown in 1827 of pollen grains moving around in a microscope seemingly at random, that physical process is called Brownian motion. And then mathematicians have developed this theory of these processes where you take this limit, the limit of the size of these grid cells to 0, and you get this sort of random process that has also been named Brownian motion, or the Wiener process. Okay, so we've already talked about a couple of examples of where random walks are useful. Stock prices. You can think about pollutants getting dispersed in the air. If the air is calm, then you have some molecules living in the air, and they have some sort of random motion because they're bumping into air molecules effectively, and they'll gradually spread out. And this diffusion process is important at the sort of microscopic level. And you can also think about, in a very different context, about neutral genes that are neither good nor bad. How do they spread through a population at some kind of diffusion process as well? Okay, so what's the simplest way we could model this kind of random motion in space? So we have something that's moving in time and in space now. So we haven't really had that before. We just had, we modeled radioactive decay or recovery of individuals. They just had a state that was on or off. Now we actually have a state, a sort of internal variable for each object that is a position in space that can change, all the time, and can become arbitrarily big in either positive or negative. And so this is a very different situation. You have really two variables, space and time. So let's look at the simplest possible version, which is called literally simple random walk, where we just take values plus or minus 1 at each step on the real line. So we're basically living on the integers. Say that we start at 0, and a particle will jump left with probability 1/2 and right with probability 1/2 at each step.
So let me get this straight. So before you were moving in 2 dimensions, that was your space.
Yeah.
Now your space is just one-dimensional, for starters, simplicity.
That's right. Yeah. We're simplifying down to the simplest possible situation. And so we're just jumping left or right. So that's almost the same as the Bernoulli random variable that we've been looking at, except the Bernoulli random variable takes the value 0 or 1. And now we want values minus 1 or 1. And we want to generate those randomly with equal probability.
So like if I got a heads, I might go right, and a tails means I go left?
Yeah, exactly.
Got it.
So there are various ways we could generate those random values. So I just did a few of them here, and I put them into different step functions. So here I'm defining the first step function. I can literally just take rand of the tuple minus 1 and 1. And as we've seen, rand, when it's given a collection, will choose one of these objects, one of these items with equal probability uniformly. And so I chose a tuple here with these round parentheses instead of square brackets, because if I had square brackets, I would be creating an array at each step. And that actually is actually quite expensive because you need to allocate memory, whereas the tuple, in some sense, does not allocate memory.
Can you add a step 5 and do that, and we could see it?
Oh, sure, good idea. Step 5 is rand of the array with square bracket is minus 1 and 1. Okay, so then now what we want to do is test how fast is each of these functions. Now, each of these functions is going to run in nanoseconds. It's super fast because we have fast computers these days. And so to actually get a decent measure of the time, what I want to do is run these functions zillions of times. Let's say 1 million times each or something. That'll take less than a second to run. And so I would need to write a little piece of code that ran these functions and calculated the time and divided and took the mean and whatever. And so that has already all been done for us in this benchmark tools.jl package. So packages, remember, are just functions that somebody has written. It's just a collection of functions. And one of the functions, or actually a macro, is called @btime. So B for benchmark and time. So it's literally it's literally what is the benchmark time. And so I just give it a piece of Julia code and it will run this Julia code lots of times and take some kind of statistics of it and report that back to me.
Is it worth slowing down for a second and just like, I always have to think this through, like a millisecond is 1/1000th of a second, right? A microsecond is a millionth.
Yeah, so
a nanosecond is like is 1
10 to the -9 seconds.
Right, 1/1000th of a second.
Yeah.
That's
1 billionth in the American interpretation of the word.
And 10 to the -9th in anybody's interpretation. That sure seems like a very small unit of time.
Yeah, it's very, very fast. Yeah, if you think about it, computers like this laptop is something like has a 2 gigahertz processor. What does that mean? Giga is 10 to the +9. And so that means it's doing 2 times 10 to the +9 operations per second. And so each operation takes about 10 to the -9 seconds, in other words, 1 nanosecond. And so here the times that it's reporting are actually on the order of 6 nanoseconds. So it's taking about 6, I don't know, clock cycles or something. I'm not an expert on this. Maybe Charles can help us out to do this rand of -1,1. So somehow it's doing some calculation which we haven't gone into in the course about how do you generate randomness, and then it's just picking one of these using that source of randomness.
I understand computers have little coin flippers inside. There's somebody with a little person with a coin inside flipping.
That's right. So this is in order, these 4 functions, and I added this 5th one. Let's see how well that does. So in order, these are the results. So this is step 1, step 2, step 3, step 4, and step 5. And so you can see that, okay, firstly, step 5 is just really super much slower. It's like, so you can also see that when I run it again, these times are not that stable. It's actually very difficult to do these benchmarks in an accurate way because the times are so fast. And because, when I run this calculation, it's competing with all the other processes that are going on at the same time in my computer, like broadcasting over Zoom. And so that's going to affect the times a lot. But so this is just going to give us a general kind of idea. And what we can see is basically, this array one, I claimed that it was very slow. And now we're actually seeing that, oh yeah, it's ridiculously slow, right? It's like roughly 5 times slower than the others, or even more. Whereas the others are sort of all the same order of magnitude, but this sign of rand n is kind of a bit slower than the other ones. And then the other ones are more or less the same speed. So let's run it again. And excuse me. Excuse me. And so you can see that, okay, the time changed a bit, but basically, yeah, it's actually difficult to say between the first 3 which of them is the best, because they kind of change order each time you run. So that basically, I would say they're roughly the same speed. And then the 4th one is definitely, say something like 40% slower. And then the last one is just orders of magnitude slower, and order of magnitude slower. Okay, so what are we actually doing here? So, for example, this one, rand less than 0.5, we know that generates true or false with probability 0.5. And then we're using that as if it were an integer value. We're multiplying it by 2. That gives me either 0 or 2 with probability a half each. And then I'm subtracting 1, and that gives me -1 or 1. So you can see that, you might want to, and this random bool that literally generates a random Boolean value, so true or false. So you can see that is, roughly the same speed as doing this. So who knows exactly, you can go and check exactly what's going on, under the hood by looking at the source code. But of course, out of all of these options, which is the easiest to read? It's this one. And so I would actually definitely prefer that, just because we see that it's roughly the same speed and the code just looks so much easier to understand. Okay, but definitely this is a good message to realize that if we can avoid making arrays with square brackets, we should. And one way is to just make tuples instead. And yeah, okay. So now that's just one step. So now we want to simulate a random walk in one dimension. So we want to do lots of these steps one after another. And we're going to call that the trajectory of a random walk. So let's make a function that's called walk1d that just literally does that. So it'll take a number of steps n, and then we'll start off somewhere, let's say 0, start off at position 0 as an integer, and we'll store that position in some vector of all of the positions x, which are called x's. So this is a vector which starts off with just this one entry, and then I'll loop through the n steps of my walk, and I'll add the result of a step. I'm calling the function step. Remember, to call the function, we need these parentheses. If you don't put the parentheses, it's just the object that is the function step one. And then I'm adding that onto the current value of x, and I'm adding, I'm accumulating, I'm like putting that at the end of the x's array. And so I'm accumulating the values of x as I go along, and then I'm returning that vector. And so if I just do sort of x's equals walk1d of 10, that actually gives me the coordinates of my random walk as it moves along. And if I run it again, of course, I'll get different ones. It can go negative, etc. And so as usual, humans are bad at looking at these numbers. And so let's plot them. So here it is a plot of 10 trajectories of 100 steps each of those random walks. And I'm just going to run it a few times, and we can see that, oh yeah, those start to look like stock prices, right? These are 10 different stocks, and they all started off at the same price, but because of the market effects, etc., they're all doing different things. And if I just increase the number of stocks or random walks to 100, sorry, you can see that something interesting starts to happen, which is that we get a kind of shape, some kind of shape that's spreading out at some rate as we move along in time. So time is on the x-axis. Let's just add that. That didn't work because I forgot the exclamation mark. There we go. So that's as we move along in time. This is the position in space, right? So let's add a y label, which is position in space. This is sort of, so I've been thinking of it as the x position in space. So x position in space. Sorry. There we go. So we're literally, each of these is moving along, but they're spreading out. So some of them are, by time 100, some of them are actually around 0 again, but some of them have already got out to position 20. But none of them has got anywhere near, for example, position 100. Why is that? Because to get to position 100, that's possible, but they would have to move left or right at each time step. And at each time step, that has a probability of 1/2. And so the probability that they'll actually reach position 100 is 1/2 to the power 100, which is a tiny number that we'll never see. And so there are lots of interesting theorems about, how far does this cloud actually spread out, right? So I can, let's run it for a bit longer, 1,000 steps, that's 1,000 walkers, that wasn't what I meant. But anyway, that's 1,000 walkers, and you can see that, okay, yeah, the shape starts to take shape. And so you can actually, again, ask, well, what happens if I just took more and more and more walkers? What would the shape be? And you can start to ask theorems about that, and that's related to the central limit theorem that we've already seen. If you think about, yeah, okay. But what I wanted to do was actually take longer trajectories. But you see, of course, we could add sliders to do this, and we get something like that, and you can see that there's some concentration around the middle, and then there's fewer around the edges, etc. And you can ask, well, as I said, well, what's this sort of function that describes how far we are away? And there's a theorem called the law of the iterated logarithm that does that. Okay, so that's great, but that's only in one dimension. But we started off in 2 dimensions. So now let's think about how we could simulate a random walk in 2 dimensions. So what do we need to change? So if we look at this walk1d function, it's pretty specific to 1D. Or is it? So what is specific to 1D? So the initialization is specific to 1D. As I said, it started at the number 0. This is not specific to 1D. If I have an x that represents the position, this will make a vector of objects of that type, whatever that type is. This is using Julia's, I haven't said anything about types explicitly in this function. But then step 1 is also specific to 1D because that was, that we designed to do a step in 1 dimension. Everything else is basically not specific to 1D. And so what we want to do is turn this code into something that is generic. In other words, that the same piece of code will work for any random walker that does anything, right? So, for example, it could, jump. It doesn't even have to live in the integers. It could jump a distance that was a number distributed uniformly between -1 and 1, a real number, and then it would live, on the real numbers.
You mean you don't have to copy and paste code for every new situation and just edit it a little bit?
Yeah. So okay, that's a good idea. So let's copy and paste this code, and make it walk 2D, and then we would have to go and change this. Oh, I'm going to start at sort of the vector 0, 0 or something. And then, but now I want to do 3D. So now I'm going to copy and paste that code again. And then, oh no, now I decided that I want to, do something extra inside this walk 1D function. Oh, now I'm going to have to copy it again in 2D and 3D. And that just gets, I've spent too much of my life doing things like that when I didn't understand software design, software engineering, and it's really nasty. So you don't want to do that.
I mean, I think that's such an easy temptation. I mean, I think we've all done it until we've learned not to.
Yeah. So I mean, to some extent, I would say that, I always say if you need to do something twice, just copy and paste. But as soon as you find yourself doing it a third time, you need to think, oh, is there some way that I could rewrite my code so that the computer automates this thing that I'm trying to manually automate, right? That's what computers are good at. So let's try and think about that. So I want to write a function that I'll call trajectory that works for any random walk. So one way of doing that is not in the current version of the notebook is the following. So let's call this function step instead of step 1. And instead of x equals 0, let's make this into, I don't actually want to modify this version of the function. Let's make a new version of the function. I'll just call it walk of n. And I'm going to say x equals initialize and x plus equals step. Right? So if I do that, then if I try and run this function, of course, it won't work because it doesn't actually know what the initialize and step functions are. So let's just write those. So initialize equals 0 and step equals rand of -1, 1. So once I've written those functions, initialize with an I. Once I've written those functions, now that code works, right? So I have at least replaced the sort of explicit call in this function with another function. And now how can I actually make this generic? How can I, what does that mean? It means I need to be able to tell Julia which initialize function and which step function I actually want to use. How can I do that? So although I've defined these functions just now, well, what I could do is actually, I want to be able to replace these functions with different function names, right? So I want to actually, let's do a 2D version of this. So initialize 2D equals, let's just use vectors for now, for simplicity. Step 2D, so it's a vector 0, 0. It's going to start at the origin in 2 dimensions. And now step 2D is going to choose a random direction in 2 dimensions. So we could do that like this, rand of the vector 1, 0, the vector 0, 1, the 4 different cardinal directions of the compass in 2 dimensions, -1, 0, and 0, -1. To do that, and that's going to choose a random 2-dimensional thing. But okay, so it looks like what I have to do is copy and paste this code, call it walk 2D, change this to initialize 2D, change this to step 2D, and then that'll all work. That's great. I can now call my walk 2D function with 10 steps, and it doesn't work because I needed rand of the vector of those vectors, right? So that's the first time I think that we've seen a vector containing vectors. Right, so you can see that there's a vector, and what is inside is the things that are separated with commas, and the things that are separated with commas are vectors, right? So if I I could call that directions equals this vector, but I need it to be a vector of vectors, and then what is the type of directions?
Would it be faster to have a tuple of directions like you showed us before?
Say that again?
Why not a tuple of directions like you showed us?
Oh, why not a tuple of directions? That's a great idea. Yeah.
You claimed that was faster, so
Okay, I could do that. Yeah, but I mean, the fact that I'm actually using these arrays is already going to be slow, so it doesn't actually matter.
I see. It's already polluted by the inside, so the outside.
Already polluted because every time what I'm doing is creating a new array of one of these. Is that true? Yeah, I think so. So you can see that what is this type of this thing? It's a vector of vectors. So by the way, I'm using Julia 1.6, which I don't think we said has actually now been released a couple of weeks ago, maybe 1 week ago. So now you can just download Julia 1.6, and that has this nice new printing that it's vector of vector, and it's telling me that that's just an alias and another name for array of array with one dimension, which is harder to read. This is much easier to read. It's a vector of vectors. Okay, and by the way, in order to have better performance, I can also make this const, which means constant, and that just makes things faster in Julia if you use global variables, which you actually really shouldn't.
Maybe I should say a word about switching to 1.6. I think in previous years, by the way, you want to type version info somewhere? I think in previous years, I would never have recommended switching in the middle of the semester. It would be a recipe for disaster. But I am, a little bit fingers crossed, but 99.99% confident that it would actually cause you no trouble whatsoever.
Hopefully, yes. So yeah, this capital, this word version in capital letters is a feature of Julia, which tells you which Julia version you are using. And that is so it gives you this answer 1.6, but that is actually a string, right? Because it's in quotes. And you see this little V in front of the string, that's a non-standard string literal, just like we saw a couple of times ago. So this is a special sort of string object in Julia that represents a version number for a package.
Okay. I always type version info. Oh, but
sure, there's a function called version info. So you need to put in parentheses because it's a function, and that will tell you all kinds of
you need it with terminal
information about your function, except that you need with terminal do to print it out. Rather than printing it on the terminal where you launched Pluto from, it's now going to record that information and put it here. So you can see which platform I'm on, which Julia version I'm using, and all kinds of extra stuff that you probably don't really want to know about. Okay. So now I can put rand of the vector directions, or the tuple if you prefer, and it will, so step 2D, when I call it, right, this is the nice thing about having an interactive environment. I can just check, does my function actually work? I'm just going to run it a few times, and it's returning a random direction. It seems to be working fine. Okay, so now I should be able to call my walk2D function, and there it is. Walk2D does a two-dimensional random walk, right? So it starts at 0, 0, moves to -1, 0, moves back to 0, 0, etc., and it's sort of gradually moving on average sort of away from 0. But now I want to do my walk 3D, and I'm going to have to rewrite this function yet again. And so that's no good. So what do we want to do? We want to actually make a generic walk function, which uses an initialized function that I specify and a step function that I specify. And the way I can do that is actually to pass those functions as arguments to my walk function. So I can do this, initialize, comma step. And now when I call initialize inside this function, it will realize, oh, initialize, that must be referring to this argument that I'm passing into walk. And it's treating it as a function, and it's going to call that function. So when I define this walk function, I'm now going to have a walk function where I'm going to pass in initialize, which is this. Let's call it initialize 1D. Where was that? I've totally lost track of where my functions are. I don't even see it now. Anyway, whatever. So I can pass in the initialize 2D function and the step 2D function and 10, and it will do a walk in 2 dimensions. If I passed in initialize and step, which are the 1D versions, it does a walk in 1 dimension. Let's just put that on a different line. Okay, so that's the 2D version, there's the 1D version. So I've written a piece of code which is totally generic. It works with any initialized function and any step function, provided this operation is actually allowed, right? So I have to have a step function that returns an object which I can add to the current value of the object x. And that's why I actually used vectors in, the directions vector. Because if I had used tuples inside the directions vector, I would be trying to add two tuples together, and that does not work. So 1, 2 plus 3, 4 is actually not defined. I cannot add tuples in base Julia. I could add them with dot plus, and so I could actually change this to be dot plus equals step, and then it would work if I put tuples in there. Okay. So you might like that version, and I kind of like it, but there's still something missing, right? If you think back to last lecture, what is missing? Well, I cannot actually talk about, oh, I have a two-dimensional random walker. Where in my code is there a two-dimensional random walker? Well, it's encoded in the fact that the position of the random walker is a vector, and the initialize function returns a vector, and the step function returns a vector of the same type. But it's all sort of delocalized, it's spread throughout my program. So what I want to do is concentrate all of that information into an object, which is called a 2D random walker. So that's what we need to do. So how can we do that? We follow a similar idea to what we did with random variables last time. In fact, this is very related to random variables. These things are sort of random variables, sort of more general kind of random variables. Okay, so let's make it more general. So we want to make a random walker object. So we know how to do that now. Struct walker 1D. That's going to be my one-dimensional random walker. It has a position, which is going to be an integer, and a 64-bit integer. And what I'm going to do is, just like last time, we made an abstract type, which was random variable. I'm going to make an abstract type, which is walker. And I'm going to assume that any walker has something inside called position. So I'm going to assume that in general, walkers will have an attribute or a field called pos for position. And then I'm going to make a function, position, which acts on any object of this abstract type walker. So this is supposed to tell me what is the current position of any kind of random walker. And the answer is, well, it's going to extract the field pos from my object called little w. And then how do I do a step of a 1D walker? Again, I'm just going to generate a random number from those positions. And so, so I can generate a walker 1D I can create one by just calling the constructor. So let's suppose it starts at 0, but it might not, right? I mean, I could have it start at 10 instead. That's okay, I can do that. And of course, I could make a constructor that takes 0 arguments and fills in the position as 0. And then I can just need to begin there, and then it works, hopefully. Yes, and then I can instead make just walker 1D with nothing inside, and it will put in the 0 for me. And then I can see, okay, well now, how do I step that walker? So step of W is going to return just how the walker needs to jump. And so what is missing in this prescription is, well, how do I update the value, right? How do I change the value of walker? How do I change its position? And so let's try the most natural thing, which is w.pos equals 1, right? Okay, or equals -1 in this case, right? Because it's jumping left. And I'm going to try that, and it gives me an error. And says me that an immutable struct of type walker 1D cannot be modified. So when I use the word struct, it creates an immutable object, which means unmodifiable. I cannot actually change the values that live inside the object. And so it seems a bit pointless because, then I can't do dynamics of a walker. So why did I, so I could have made it mutable by writing mutable struct walker 1D, and then I would have been able to change it. So let's just try that. So let's make a mutable struct called a mutable walker. Now, if I make walker called W2, which is mutable, and I make its value 0, now I can reach inside and sort of manipulate its internal organs and change its value to -1, and it moved. Okay, so that is definitely one possible approach you could use. That's often the approach we've used previously in previous years. But actually, I would like to show the opposite version, where we actually do not do that, and we make a new object at each moment, right? So how can I update this? I can't really update it, but what I can do is say, okay, so I have my immutable walker 1D object. I cannot change the value that's inside that walker 1D object that's living in memory somewhere, or maybe it isn't even stored in memory. That's the advantage of using one advantage of using immutable structs is that you might not even need to store them in memory. They could just sort of live in the CPUs as sort of registers or something. So how can I change the value of W? I can just make a new walker 1D object with a new value and assign it to the same variable W, although in Pluto, I can't actually do that in a different cell. So I can do it, I have to do it in the same place that I can make, of course, a new walker object, W3, with that variable. So that's a slight disadvantage of using this approach with Pluto. Okay, so what I want to do is now, so that's the approach I'm going to use. I can actually create a new object of the same type with a new value inside. So this seems like it must be expensive computationally, but actually it is not. This whole operation will just be sort of compiled away and it will disappear, and you'll just effectively, the actual code will just literally modify the value of this position. Okay, so now we need a new function, which is update. So that's what's going to update the, it takes in a walker of type, which I've called W, capital W. So little w is the walker object, capital W is the walker type. And it takes a step value. And what it's going to do is calculate the current position of W, add the step to it, and then look, what is it doing? It's taking this type W and calling it with this argument. And so it's actually creating a new object of the same type W with the new value. So that's exactly what I just did with this walker 1D of 1. But in order to do that, it needs access to this type W. And so that's why I used this Julia syntax, which is where. So what is W here? W is kind of another parameter. It's another variable, if you like. But it's a type parameter. So what I need to say is this, I'm telling it W is a type. That's because it's a type annotation here, colon, colon, W. That means W must be capital W must be a type. But I want to actually restrict that type to say, oh, that type W has to be a subtype of walker. But actually, it can be any subtype of walker. And that's basically what this where means.
So there's a lot of moving parts, and I don't know, I could get a bit confused looking at this. So could we break this down a little bit? Like in the context of this lecture, what capital W's are you talking about here? You had walkers and steps and all sorts of things.
So capital W here is sort of like walker 1D, the walker 1D object type, the walker 1D type, or the walker 2D type.
Okay, so could I see this working and being updated on both those types?
Yeah, so that's a good question.
What does this thing really do?
So I have a walker 1D type, and then I want to update it. So I'm going to pass in W, and I'm going to pass in the step that I want it to take. And what does it return? It returns a new type of walker 1D. Sorry, a new object of type walker 1D with the new value. But this is a new object. It did not modify W. W is still has this.
So let me say that back slowly to see if I've got it. You've got this W, which is a walker 1D at 0. You do update, and now all of a sudden I have a walker 1D at -1. If I updated that again, what would happen?
So the point is that I'm currently not changing the value assigned. So you can think of a variable name as kind of an arrow that points to a particular location in memory. So what I'm saying is, when I'm doing this, I'm not actually modifying the value that W is pointing to.
Yeah, I see that. Well, W is still at 0.
It's still pointing to the same thing that it was before. What I have done is created a new object somewhere else in memory, conceptually at least, and some, that new object has the new correct value. And so now what I want to do, I would like to do W equals the result of updating W. And I want to make W point to that new object instead. But I can't do that in Pluto.
That's a Pluto problem, right?
That's a Pluto.
If you were in the REPL, you could do it.
Yeah, if I were, exactly, if I were. But what I can do is I can do that within a function. So let's write the function.
Wait, I'm not ready for a function. So your examples make me think this only works on Walker 1D.
Right, so let's do it with Walker 2D. So let's call W2D a Walker 2D with position -1, -1.
Why do you make it 0, 0 to be analogous to the other one?
Sure, 0, 0. That doesn't work. Why doesn't that work?
Is it little d? I forgot.
Oh, I haven't defined Walker 2D yet.
Oh, that's a problem.
So how can we define Walker 2D? So I decided to actually define it in a different way. So I could have defined it with a vector. And then I could have just used the same idea, right? I have step that's going to return a vector, and I just add the current version of step to this version of Walker 2D. But I wanted to illustrate a point, and so I didn't do it like that.
All right, so you could go Walker 2D of left paren 0, 0 right paren.
Yeah.
By just deleting the brackets.
Okay. Exactly. So that makes a Walker 2D, and now I want to update that Walker 2D, and now I'm going to update it with a vector, -1, -1. And that makes a new Walker 2D object where it has modified both of these arguments.
So the interesting thing that you're pointing out is that if you update a Walker 1D, a Walker 1D comes back. You update a Walker 2D, a Walker 2D comes back.
That's right. Sorry.
That's sort of magical that I mean, or maybe it's obvious that that's what it ought to do. But if you go back to your update syntax, we could see exactly where that happens. That this W, this capital W in the middle of all this is a variable type. I mean, you've illustrated it with Walker 1D and Walker 2D.
So yeah, so the function sort of calls the constructor of the type W to make a new object of that type.
Yeah, that seems as powerful as it is difficult to remember how to use.
It is powerful. Yeah, when I was writing this, I was thinking, well, how can I actually make this work? And this is the way that I think you have to do it to make this work. And that's because we're using immutable objects. If you use mutable objects, you could just reach in and change the value, and that's actually much easier to do. And so
why don't you do that?
Yeah. Okay. So
no. Why are you choosing not to do that in your own implementation?
Because often, because people. Yeah, that's a good question. There's a lot of people who prefer to have functions that do not modify the objects that they're acting on, because that's actually harder to reason about. Because you can just you can call a function and it might modify something, and you don't even realize that it's modifying that, and that's actually hard to debug, and maybe it's difficult to parallelize, or maybe it's difficult to etc. And so that actually, there's this whole world of functional programming where the idea is you want to minimize the side effect. So that's called when you modify an object, it's called a side effect. So what we're doing here is creating a new object, and that's sort of much easier to analyze from a computer science point of view. So if we have mutable objects, we could have just written something like this, and we're going to use update bang. So this is a different function. It has a different function name. It has this bang on top. And that is a convention in Julia that we are modifying. That's actually sort of, a Julia program writer signaling to other people using their program that this function is special because it is modifying the object, right? So this would be a sort of W mutable. It has to be a mutable Walker now. And now we don't need that type anymore because we're not going to create an object of the new type. But what are we going to do? We're going to say let's just make this a function to make it clearer. We're going to say, I'm going to reach inside W mutable. I'm going to modify its position as its current position. How am I going to do that? Let's just say, so the current position equals W mutable dot pos. And I'm going to say new position, current pos equals W mutable dot pos. New position is current position plus the step that I'm trying to do. And then I'm going to say, okay, now update the mutable object's position, reaching inside it and modifying its internal organs. That's the way I like to think of it, equals the new position. And then that's all. It doesn't even return anything, or it doesn't need to return anything. Right, so that's easier to understand, but it's harder to analyze the program. So it's actually, it's often recommended that in Julia you try to avoid these mutable objects. You can't always avoid them, and you might get easier code to write if you use mutable objects. You can see that we don't have to go through this weird thing with this type, which we're going to use to create a new object, etc. So it's definitely conceptually easier, but it's actually, people prefer to write it in the other way. I don't know if Charles wants to say anything about that. We're almost out of time. So how can we now use that all to write this trajectory function? So a trajectory needs a walker again. So let's add this. So I'm passing in W of type capital W again, and I'm specifying that capital W has to be a subtype of walker. So this is only going to work for subtypes of walker. You might actually remove that restriction. We can discuss that. So then n is the number of steps that I want. So the first thing I do is calculate where is W right now by calling this position function. That's often called a getter function because it gets a value that belongs to the object. I don't love that name, but and then I'm going to do my loop, and so I'm going to calculate just like I just did, basically the current position. I'm going to update. And then I'm going to, you see, this is where I'm reassigning the value, reassigning the variable W to a new object. So this update is actually creating a new object of that type. It does not have a bang. It's making a new object of the type with the current W and the step function applied to that W. And then I add that to position. And so this is actually a version of that walk function. So I called it walk before, now I'm calling it trajectory, sorry. Maybe we can call that walk as well. And this is now going to be walk. There we go. So that is, now I'm passing in a walker 1D object. And what it's doing is at each step is creating a new walker 1D object. And then, but I'm only accumulating the vector of their positions over time. So there is the vector of their positions of these walker 1D objects. But the point is that this walk function is now totally generic. I don't need to pass in the functions initialize and step. This function step here is what I specify for each new walker type that I introduce. So for example, here's a 2D walker, as I said, with X and Y separated instead of in a vector. So what is the position of the walker? I'm actually decided to return a tuple. And then what does step do? It returns this vector, just like we did before. But now, how do I update? Well, update now has to know about exactly the internal representation of position and the internal representation of step. And I chose these two different representations to make a point, which is that now I have a specialized version of update and a specialized version of position, actually. Right? Because before I said that, oh, the position of any walker object, any object or any type of walker is just going to extract the pos field, the field called pos, from the object. But now I don't have I chose not to have a pos field for this purpose. And so I actually make a specialized method that only works for walker 2D, where it returns something else, which is the vector of these two variables that are stored inside. And then, so that's an example where I'm sort of telling Julia how to specialize these functions that I'm using in my generic code just for this particular type. And then now I need an update function too, because the update is special too, because I have these two different representations. The representation has two values and the representation is a vector. So here I, how do I change the x coordinate? I add the first component of the step vector to w dot x and the same in y, and I return my new Walker 2D. And so when I do that, it all works. And so that's an example, I think it's a good example of generic programming, where this function doesn't change. All that I change is I specify each of these functions that I need for my Walker object, for the new type of Walker object. And I can basically do the internal representation however I want. And this function still just works. Is that clear? I know it's a bit intricate. If we really wanted to just simulate a two-dimensional random walker, we don't need to go through all of this. And we could have just copied the walk 1D function and made a very simple walk 2D function instead. But I think this is very illustrative of how you actually go about really building up more complicated pieces of software. Okay, so unfortunately we're out of time. So there's a little couple of more topics that are very interesting that we can do next time. Okay, thanks everybody. So see you on Tuesday, Monday. Sorry, see you on Monday.
Next Monday, yep. It's April next Monday.
Okay, bye. Have a